Hey everyone, it's Fabiology here. We're talking about data. It is a data discussion because that's what we have to do with our AP tests, especially FRQs. They have a huge section about experimental design and looking at data and graphs and what do these error bars mean and give some sort of statement about them. So let's just get right into it. Here are our goals today. We want to be able to state the use of error bars. We want to be able to make claims based on statistical error and explain ultimately why this comic is so funny, right? Hilarious. Sorry, dude, we just can't trust you. What does that even mean? But as you get a little smarter, this joke gets a lot funnier. It's a hoot. Okay, so here we go. Experimental design vocabulary overview. What we want to talk about here is standard error. This is the variability in a data set. So when we think about every trial we do, there might be some sort of error because the more data you take, something is different every time, whether it's ambient temperature or let's just say for your cooking, for example, you measure out 1 cup of broth to make your soup. You make your soup, the next day you do it again, but you measure out, but you use a different measuring cup. Or you slightly change the recipe by mistake. You added a little bit too much salt this time, okay? So like that's the idea, is there's some sort of small error in every time you do the data, okay? That's standard error. And standard deviation is also coming up. That's the spread of data. So think of that bell curve. That's the range that your data is in. So if you have a high standard deviation, it means that your data is really spread out. So that makes it a little bit less reliable because if you think about it, if your data is really clustered together, it's going to make this like nice bell curve really shrunk in, right in one spot. But if your data is really spread out, that makes a really hard claim, okay? And so then we'll also use this term statistically significant, and that's how we start to say that data is showing a relationship. And then the null hypothesis or the no hypothesis. There's no relationship, there is no effect. So if they ever ask you to write a null hypothesis, you literally would just say the blank has no effect on blank. That's literally what a null hypothesis is. All right. Now we got that out of the way. These are some great examples of what error bars look like, okay? So you can add them to a variety of things: scatter plots, line graphs, bar graphs. And so oftentimes we use the average. And what we interpret from this is if we have an error bar, it's a plus or minus. That's why you see it on both sides. So adding error bars shows that variation, that plus or minus in values. So, for example, if we look at something like, let's say this one over here, right? If the average value is 6.5, but there's a 0.8 error, then the range in values is or averages is really 5.7 to 7.3. Okay, that's really what it's trying to show you, is that up and down percentage there. And then we have some error bar analysis. Now I love this. This is from some website called Biology for Life. You should check it out. There's a lot of great stuff there. But when we look at things like overlap, less overlap, and no overlap, this is the quick things you want to be able to do when you're looking at your AP test. So if there's any overlap at all, you can basically say that there's not statistically significant evidence that there's a relationship, or there's no statistically significant evidence because of some sort of overlap. Now, when there's less overlap like this, then we may have to do a chi-square test or a t-test, another statistical test, to confirm that there is no statistical relationship. However, the quick and easy for like AP is to just straight up not statistically significant. But when there is no overlap, that's why we can say they're statistically significant. Especially, notice there may be a lot of error in here, but the error bars are so far apart and there's that giant gap that there is still some sort of relationship going on. And so that's why we can say it's statistically significant. So one of the things I really encourage you guys to do is have these sentence frames in your back pocket. So if it was me taking the test, I would say something like, if we're looking at, like, let's say this first one, analyzing the error bars, we see the bars overlap, which means our data isn't statistically significant. And then maybe it asks you more about what you could say with the null hypothesis. Now we can say, with the error bars overlapping, we can reject the null hypothesis, or excuse me, we would accept the null hypothesis because the error bars overlap, right? Because we have to reject it if there's no overlap, okay? When there's no overlap, that means something happened by more than by chance. That's really what it comes down to, okay? So use these accept, overlap, do not overlap, isn't kind of like sentence frames to help you think about what's going on, right? So if I was doing it for this one, I would say, analyzing the error bars, we see the bars do not overlap, which means our data is statistically significant. We can reject the null hypothesis because the error bars do not overlap. Boom. 2 straight sentences, 2 solid points probably on the AP test. And then we might see it also in a data table. So when we think about it, is where is the standard error? Well, we see a little bit right here, right? A little plus or minus 0.5 millimeters, okay? We see our overall averages, okay, from the 2 trials. And then we want to think about what's the standard deviation? This is overall standard deviation. And so when we think we have small sample size, there's only 2 trials, it's really hard for us to get a good picture what the standard deviation is really telling us, but it is kind of a large number. And so for us, we may say the standard deviation is a larger number, so therefore maybe it's not as reliable. More data would tell us more results. So sometimes on the AP test, they ask you to do a little bit of some of that analysis in that sense. Like, what could the experimenters do differently to improve their quality of experiment? So there we go. Do we now know why this is funny? Right? So that's our mastery question. Let's explain this comic in a science and mathematical term, some smath, science math. Why is this funny? Explain using terms from the video to help you out with that. All right, guys. Thank you so much, and have a good one.